Welcome, everyone. In this presentation, we are going to explore the concept of mixture of experts, commonly abbreviated MoE. MoE is an architectural idea designed to dramatically increase model capacity without proportionally increasing computation for every input. Instead of activating all parameters for every token, like a traditional dense model, MoE activates only a small subset of specialized subnetworks called experts. This allows the model to be both large and efficient at the same time. Throughout this talk, we will cover the intuition behind MoE, how routing works as an intelligent decision system, how MoE layers are structured inside modern transformer models, and why load balancing is a crucial engineering challenge. By the end, you should understand not just what MoE is, but why it has become a key technique in scaling today's largest AI systems. Let's begin by defining what a mixture of experts model actually is. At its core, MoE is composed of many smaller neural networks, known as experts, along with a gating or routing network. Each expert is capable of learning different patterns, features, or types of data. The gating network's job is to decide for every token or input example which experts should be responsible for processing it. Importantly, only a few experts are activated at a time. This means the total number of parameters in the model can be extremely large, while the actual computation per token remains manageable. This sparse activation mechanism is what makes MoE so attractive for scaling. Instead of one monolithic model trying to handle everything, we have many specialists, and only the most relevant ones are consulted for each piece of input. A helpful way to understand MoE is through the analogy of an expert committee. Imagine a panel of specialists where each person has deep knowledge in a specific area. When a new problem arrives, a coordinator listens to the question and decides which expert should respond. Not everyone speaks at once. Only those with relevant expertise contribute. MoE works in a very similar way. The router acts as the coordinator, examining the representation of each token and selecting the experts most likely to process it effectively. Each expert then produces an output, and these outputs are combined to form the final result. This committee-style collaboration allows the system to be both flexible and specialized, which is difficult to achieve with a single uniform model. Why not simply use one very large dense model instead of all this complexity? The key issue is that dense models apply the same set of parameters to every input, regardless of whether those parameters are relevant. This can limit specialization and waste computational resources. In contrast, MoE introduces conditional computation. Different inputs can activate different subsets of parameters, allowing the model to specialize internally. This means the overall parameter count can grow to an enormous size, improving representational capacity, while the per-token computation grows much more slowly. This property is essential for modern large-scale AI systems, where we want both high performance and practical efficiency. MoE provides a scalable path forward that dense architectures struggle to match. Summarizing the core advantages of MoE, we see a powerful balance between scale and efficiency. First, MoE enables massive parameter counts, allowing the model to store a huge amount of knowledge. Second, because only a small subset of experts are active per token, the computational cost of each forward pass remains relatively low. Third, experts can specialize in different domains, patterns, or languages, leading to improved performance on diverse data. Finally, MoE architectures have proven to be a practical way to scale models into the hundreds of billions or even trillions of parameters. These properties make MoE one of the most important innovations in large model design in recent years. Now let's move into the concept of routing, which is the mechanism that makes MoE work. Routing determines which experts will process each token. This decision is made dynamically and individually for every token during both training and inference. The component responsible for this decision is called the gating network. It is typically a small neural network that looks at the token's hidden representation and outputs scores for each expert. Routing is what enables sparsity because it ensures that only a limited number of experts are active at any given time. Without routing, MoE would simply be a large ensemble with no efficiency benefits. With routing, however, we get conditional computation that adapts to the content of the input. Let's take a closer look at how the gating network actually scores experts. The token representation coming from the previous layer is fed into a linear or shallow neural transformation. This produces a set of LOIDs, one for each expert. These LOIDs represent how suitable each expert is for processing the token. A softmax function is then applied to convert these LOIDs into a probability distribution. Experts with higher probabilities are considered more relevant. These probabilities are used both to select which experts will be active and to weight their outputs later. Even though the gating network is relatively small, it plays a crucial role in shaping the model's behavior by controlling how computation is distributed across experts. In practice, we do not send each token to all experts. Instead, we use a top K selection mechanism. This means that for each token, only the top K experts with the highest routing scores are chosen. K is typically a small number, such as 1 or 2. This keeps the computation per token low, while still allowing the model to access a very large pool of parameters overall. The selected experts receive routing weights based on their probabilities, and their outputs are scaled accordingly. Experts that are not selected are completely skipped for that token. This top K strategy is a key design choice that balances efficiency and model capacity. You can think of routing as an intelligent dispatch system in a large computing center. Instead of sending every task to every machine, the dispatcher examines the task and assigns it to the machines best suited for it. In MoE, different tokens in the same sentence may be routed to different experts depending on their content. This creates a fine-grained, content-aware computation pattern. Routing allows the model to adapt its internal processing pathways dynamically, which is fundamentally different from dense models where every token follows the same path. This flexibility is one of the main reasons MoE models can achieve strong performance at scale. Let's now examine where MoE fits into a transformer architecture. Typically, MoE layers replace the standard feed-forward network, or FFN, layers inside each transformer block. The self-attention layers remain dense and shared across all tokens. After the attention step, instead of sending tokens through a single FFN, they are routed to multiple expert FFNs. A gating network sits between attention and the experts to make routing decisions. This design preserves the powerful sequence modeling ability of attention, while greatly increasing the capacity of the feed-forward component. The result is a sparsely activated transformer that is much larger in parameter count than a dense one with similar computational costs. Looking inside a single expert, we usually find a structure very similar to a standard transformer feed-forward network. It typically consists of 2 linear layers with a nonlinear activation in between, such as ReLU or GeLU. What makes experts special is that they do not share parameters with each other. Each expert learns its own set of weights and therefore can specialize in different types of patterns. Some experts may become better at handling certain syntactic structures, others at particular semantic domains, and so on. This diversity of learned representations is what gives MoE its expressive power beyond that of a single dense FFN. Understand the full data flow inside an MoE layer. Let's walk through it step by step. First, tokens pass through the self-attention sublayer as usual. The resulting representations are then fed into the gating network. The gating network computes routing scores and selects the top K experts for each token. Tokens are then dispatched to their assigned experts, where they undergo feed-forward transformations. Each expert produces an output which is then weighted according to the routing probabilities. Finally, the weighted outputs from the selected experts are combined and passed on to the next layer. This dynamic routing and merging process happens for every token at every MoE layer. The idea of sparse activation is central to MoE. Even though the model may contain dozens or hundreds of experts, only a small number are active for any given token. This means the effective computation per token is much smaller than what the total parameter count might suggest. Sparse activation allows us to dramatically increase model capacity without linearly increasing the number of floating point operations. In other words, we can build extremely large models that remain computationally feasible. This is one of the key reasons MoE has become such an important technique for scaling modern AI systems. Despite its advantages, MoE introduces new challenges, one of which is load imbalance. Because routing is learned, the gating network may start to favor certain experts over others. Some experts may receive a large fraction of the tokens, while others are rarely used. This leads to uneven training, where popular experts get many gradient updates and underused experts learn very little. It can also cause hardware inefficiencies, since overloaded experts become bottlenecks. As the number of experts grows, this imbalance problem can become more severe, making load balancing a critical aspect of MoE design. Load imbalance can have several negative consequences. Overloaded experts may become computational hotspots, slowing down training and inference. Underutilized experts, on the other hand, waste parameters and fail to develop useful capabilities. This uneven distribution of work can also lead to unstable training dynamics, as gradients are not evenly spread across the model. Furthermore, in distributed training settings, imbalance can cause poor utilization of parallel hardware resources, reducing overall system throughput. Addressing these issues is essential for making MoE practical at very large scales. To mitigate load imbalance, several techniques are commonly used. One of the most important is an auxiliary load balancing loss added to the training objective. This loss encourages the routing distribution to be more uniform across experts. Another strategy is to impose capacity limits, restricting how many tokens each expert can process in a batch. If an expert exceeds its capacity, excess tokens may be rerouted or dropped. These mechanisms help prevent a small number of experts from dominating the workload. By gently guiding the router toward a more even distribution, we can maintain both efficiency and model quality. When load balancing works well, the benefits are significant. Experts receive a more even share of training data, allowing them to learn meaningful and diverse representations. No single expert becomes a persistent bottleneck, improving computational efficiency. Hardware utilization becomes more predictable and balanced, which is especially important in large distributed systems. Training also tends to be more stable, since gradients are spread more evenly across the model. In short, effective load balancing is a key ingredient that allows MoE models to scale reliably to extremely large sizes, while maintaining both performance and efficiency.